Okay, look at translation and vectors. No, not him. Mathematical vectors. We already know that a translation is a transformation that slides the pre-image onto the image. Here are some properties of a translation. If we have a point P and Q that are just translated, they just slide. The distance that they slide is the same, so those two things are congruent, and they're also parallel. And then that gives us, I guess, P prime and Q prime. P prime and Q prime. So P to P prime, that's congruent to Q prime, those segments there. Remember when we write them without the bar on top, it's talking about the distance, the length. And then another thing is that those two segments are parallel. So that makes sense. You're just sliding it, so why wouldn't they be parallel? This and that are just parallel. All right, cool. Moving on. I guess we can write down a note that we already know. A translation is an isometry. And that just means that all lengths are preserved, all angle measures are preserved, all distances are preserved, and parallel lines are still parallel. We are going to have some transformations that don't preserve these things, that may like shrink the pre-image or like grow the pre-image. So, yeah, translations are isometries. Okay, let's take a look at the...
What if I talk like Bane for the rest of the video? Here's another theorem.
I don't want to do that for the rest of the video. If lines K and M are parallel, so if these lines are parallel, and then a reflection in line K, so this reflection from here to here, if you have that reflection, and then reflect it over line M, it's the same thing as a translation from Q to Q double prime and P to P double prime. So that's P to P double prime. It's the same thing as if we just translated it, and the distance would be double the distance between the parallel lines. So I'm going to write that down. In other words, what if he was unsure of himself? He's just a bumbling, never mind. So, let me read it again. If you reflect a pre-image twice over two parallel lines, so reflect, and to get to that third one, then it's the same thing as if you just translated this. Oh, how far did you translate it? Well, just you take the distance between the parallel lines and you double it. That's how far you translate. That's how far? Yeah, that's how far you translate it. Who are you? I'm leaving. Okay, that's weird. Okay, this example says translate A, 3, 2, 2 units to the right and 5 units down. Okay, so 1, 2, and then 5 units down. 1, 2, 3, 4, 5. Okay, so that's A prime. That's pretty easy, but it also says then write using coordinate notation. So I guess we can find the ordered pair for this. This would be... Actually, no, before we do that, coordinate notation, it looks like this. If you take an x and a y, x comma y, you can translate it by saying how much you moved left or right, how much you move horizontally. Here we moved 2 units to the right. That means positive, right, because to the right is positive. So x plus 2, and then 5 units down, that's in the horizontal direction, so that goes, no, that's in the vertical direction, so that goes up and down. So you use the y, and it's downwards, so that's negative, minus 5. So that's coordinate notation. And the way, well, let's see if it actually works. Let me count to see what that coordinate is. If I go for my x, I'll have 1, 2, 3, 4, 5. And then for my y, I have what, down 1, 2, 3, negative 3. Okay, like that. And if I just take these, let's see. I mean, I can see. First, I start out with 3. 3 plus 2 is 5. Oh, look at that! And 2 minus 5. Well, 2 minus 5 is negative 3. Ho, ho, ho! Woo, we got it! So that's just two ways to do stuff like that. Okay, a vector, I guess we're talking about vectors now. It's another way that we can actually write, instead of coordinate notation, we can describe a translation using vectors. And a vector is just the evil villain who likes cookies and sharks. He likes sharks. No, wait, no, that's not him. I mean, it is him, but that's not what... It looks like an arrow, okay, that has direction and magnitude. So it points in a certain direction, and the length of the arrow tells you how far you're going. Another part of vectors is something called component form, which is written like this. Instead of parentheses, you use these little pointy parentheses. Pointy parentheses, that's funny. And this, the x-coordinate, just tells you how much to move left or right. So if it's a positive number, you move right that much. So like if it's a positive 3, you move right 3. And then if it's a negative, you move left. And then this one is up and down, same idea. Okay, in this picture, PQ maps onto P prime, Q prime. Describe the translation in coordinate notation, so that's one part. And use component form for the vector, or for the translation vector. Okay, so pretty much for coordinate notation, we already know how to do that. That was just, you start out with x, y, and you just figure out how much you're moving. So I guess when P goes to P prime, how much do I have to move left to line up there? Well, let me just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. And it's left, so we go back 9. So it's negative 9. Whoops. Remember, for coordinate notation, you have to do x minus 9. And then y, for point P, moves which way? Which way? If it moves upwards, how much do I have to move up to line up there? There's 1, 2, 3, 4, 5. So it's y plus 5. So that's the coordinate notation. That was really easy. Now component form, remember, so the vector would be like this. It moves there. This is the translation vector in green. That's just, well, we write that by doing the component. So remember, the x is how much you move left, and we already decided that it was negative 9 because we moved left 9. And then up 5. So, I mean, that's just component form of this vector. I'm in the D. How come you don't do nothing with Q? Well, when we translate something, it preserves everything because translations are isometries. So if we were to do this on Q, we'd end up with the same exact vectors, just in a different initial point and terminal point. So the component form for that one would still be the same because you're just counting how much you move left, how much you move up. So it's the same thing. We could do either one, actually. I guess my two answers here would be this and this. Okay, last example. Name the vector and write its component form. So this vector, well, it has initial point A and terminal point B. Those are two vocab words. Remember, never mind. So to name this, we can just say, kind of like we name array. We have to do initial point first, so A, B. If we did B, A, like that, that would be wrong, because it's pointing, as you can see by the arrow, it's pointing in that direction. So we got to go from A to B. Okay, so that would be wrong. And the components, well, all we have to do is count. How much do we move? And we move right, so it's 1, 2, 3, 4, 5. So this would be positive 5 because we're moving to the right. And then how much do we move up or down? 1, 2, 3, 4, 5. Ooh, 5, 5. So this is the component form. This is the name. Easy. Something I want to point out is that this vector could have been in any position and it would still have this component form. Because if I had something like this, where this was also called A and B, we would have the same exact answer because we move left 5 and up 5. So they don't have to be in the same spot. I mean, vectors can move all around. Now, all they have is a direction and a magnitude. you can go from anywhere. So like you can actually draw three different positions for the same vector. So this was my answer. Let's be done. Okay? Okay.